In this video, we're going to cover the comparison test and the limit comparison test. First, for the comparison test, it says suppose that we have sigma of a sub n and sigma of b sub n are series with positive terms. If the b sub n series is convergent and a sub n is less than or equal to b sub n for all n, then the a sub n series is also convergent. Then it says if the b sub n series is divergent and a sub n is greater or equal to b sub n for all n, then the a sub n series is also divergent. And right here we have a note that kind of breaks it down. The first part, which is this one up here, says if we have a series whose terms are smaller than those of a known convergent series, then our series is also convergent. And then the second part, or this guy right here, says that if we start with a series whose terms are larger than those of a known divergent series, then it too is divergent. This example says determine whether the series converges or diverges. For part A, we have sigma n equals 1 to infinity of 2 over n cubed plus 4. We're going to consider just this formula, 2 over n cubed plus 4. What we want to do is we want to compare this with a series that we are familiar with. So we're going to use the 2 on top, and then in the denominator, we're just going to use the n cubed. So one way to look at it is of these two terms, the dominant term would be the one with the variable, so we used that one, n cubed. And when comparing these two fractions, we want to be able to put an inequality right here, either greater than or less than. And the way I usually think of it is I look at this fraction, and because this says n cubed plus 4, for this fraction, we're dividing by more. So when you divide by more, it makes the fraction smaller. So we can say that this fraction is less than this one, and that works when n is greater or equal to 1. So now what we do is we're going to consider this series, and I wrote it out here. We use sigma n equals 1 to infinity of 2 over n cubed. So I pulled this 2 to the front of sigma, and now we just have 1 over n cubed. So this is now of p-series form, and p is equal to 3, and 3 is greater than 1, so by p-series, this series is convergent. And I just wrote that out, therefore the series is convergent. So since we've identified that this series converges, and all of these terms are less than these, by the comparison test we can conclude that the original series also converges. For part B, we have the series where n starts at 1 and goes to infinity of n plus 1 over n squared. So first we're just going to look at this. We have n plus 1 over n squared. We're going to take the dominant term on top, which is the term with the variable, and then we're just going to use the denominator. Next, we want to compare these with an inequality. And again, the way I kind of think of it is this fraction has more on top, so that would make this fraction bigger. So we would say that this is greater than n over n squared. Then looking at this fraction, it simplifies and you get 1 over n, and this holds true for n greater or equal to 1. So since 1 over n squared becomes 1 over n, now we're going to consider the series 1 over n. You can think of this as a p-series where p is equal to 1 and 1 is less than or equal to 1. You can consider this a p-series, or you might notice it's a harmonic series. Either way, this series diverges. So I just wrote it out, therefore this series is divergent. And since we determined that this series diverges, and that corresponds to this n over n squared, because this is greater than that, we can conclude by the comparison test that this original series also diverges. For part C, we have the series n starts at 1 goes to infinity of 4 plus 3 to the n over 2 to the n. So first we're going to consider just this formula, and we're going to take the dominant term that's in the numerator, so that would be the one with the variable, and then we'll use the denominator 2 to the n. And to compare these, this fraction has more in the numerator, so this will be greater than this one. Next, I want to take this fraction and rewrite it. Since 3 and 2 both have the same power, we rewrite it as 3 halves all to the nth power. So now looking at this, you can see it's a geometric series. R is the constant being raised to the variable exponent, so R is 3 halves. Then we're going to take the absolute value of R, which is just 3 halves, and that's greater or equal to 1. Therefore, our geometric series is divergent. So since this series diverges, and also because we know that this series has terms that are greater than this one, by the comparison test, we can conclude that this original series also diverges. For part D, we have the series n starts at 1 goes to infinity of 1 over the square root of n cubed plus 1. So we're taking this expression and we're going to use the 1 on top and then the dominant term in the denominator. So the dominant term is going to be the one with the variable, so we have n cubed, but it's underneath the square root, so really it's the square root of n cubed. As far as comparing these, on this fraction you're dividing by more, so this fraction is going to be smaller. And then last I want to rewrite this as 1 over n to the 3 halves. So now we consider the series of this 1 over n to the 3 halves. And it works out great because this is of p-series form, where p equals 3 halves. And 3 halves is greater than 1. So for p-series, since 3 halves is greater than 1, we can conclude that this series is convergent. So since this series is convergent, and the terms of this series are less than those of this one, by the comparison test, we can conclude that this original series then converges. Next, we have the limit comparison test. It says, suppose that sigma of a sub n and sigma of b sub n are series with positive terms. If we have the limit as n goes to infinity of a sub n over b sub n, and it equals a constant value c, where c is a finite number and greater than 0, then either both series converge or both will diverge. This example says, determine whether the series converges or diverges. For part A, we have sigma, n starts at 3 goes to infinity, of n plus 2, all divided by n plus 1 quantity cubed. So we're going to use the limit comparison test. The first thing we're going to do is we're going to let this equal a sub n. So this is our a sub n, and now we need to identify b sub n. So for b sub n, we're going to take the dominant term on top and the dominant term in the denominator. So on top, we're going to use n. Down here, if we were to expand this out, our highest power would be n cubed. So that's the term we're going to use. And then finally, we'll simplify this so we get 1 over n squared. All right, so now we have a sub n, and then we have b sub n. So next, we're going to set up the limit as n goes to infinity of a sub n divided by b sub n. So here's a sub n, and we're going to divide by b sub n, which is the same as multiplying by its reciprocal. So we times by n squared over 1. Next, we're going to take this n squared and distribute it on top. And then I just left the denominator as the quantity n plus 1 cubed. So at this point, we have an infinite limit and we have a rational function. The degree of the numerator is 3, and then the degree of the denominator is also 3. Since the powers on top and bottom are the same, this infinite limit is equal to the ratio of their leading coefficients. So the leading coefficient of the polynomial in the numerator is 1. And then also, if you were to expand this out, the leading coefficient of the denominator would also be 1. So as n gets larger and larger, this limit is going to equal 1 over 1 or just 1. So since the value we got for c is positive and finite, we can now look at the series of b sub n. So we have sigma n starts at 3 goes to infinity of 1 over n squared. And you'll probably notice that this is of p-series form, where p equals 2 and 2 is greater than 1. So we get that this series is convergent. Since we determined that the series of b sub n is convergent, by the limit comparison test, it says that the original series of a sub n does the same, so we conclude that this original series converges. For part B, we have sigma n starts at 1 goes to infinity of n plus 5 over the cube root of n to the 7th plus n squared. So we're going to let a sub n equal this expression. And to determine b sub n, we're taking the dominant term on top, which is going to be the n. And for the denominator, the dominant term is going to be n to the 7th, but remember it's still under a cube root. So we have n over the cube root of n to the 7th. So we're going to rewrite this as n to the 7/3. And then finally, this is n to the 1 over n to the 7/3. So we'll simplify that. So 7/3 take away 1 is the same as 7/3 minus 3/3. So that'll be 1 over n to the 4/3. So next, we're going to take the limit as n goes to infinity of a sub n divided by b sub n. So we have a sub n, and then we're going to divide by b sub n. But dividing by b sub n is the same as multiplying by the reciprocal of this guy over here. Okay, so next we're going to take this n to the 4/3, and we're going to distribute it on top. So again, we're multiplying this to both terms. This would be n to the 1 times n to the 4/3. So again, we're going to multiply this term to both of these. When we multiply this n to the 1 times n to the 4/3, we're going to add those exponents. So really, this is 1 plus 4/3, which is the same as 3/3 plus 4/3. And then in the denominator, I just rewrote this as n to the 7th plus n squared, quantity to the 1/3 power, so that these are kind of in similar form. And again, this is an infinite limit, and I want to look at the degrees in the numerator and the denominator. So in the numerator, your degree is going to be this highest power of 7/3. In the denominator, for these two terms, we have this n to the 7th, and technically, again, it's to the 1/3. So really, the highest power in the denominator is also 7/3. So since the degree of the numerator and the denominator are the same, they're both 7/3, this infinite limit is equal to the ratio of their leading coefficients, which would be 1 over 1, or just 1. So since we got that c is equal to 1, which is positive and finite, now we consider the series of b sub n. It's of p-series form, and p is equal to 4/3. Since 4/3 is greater than 1, the p-series is going to be convergent. And since the series of b sub n is convergent, by the limit comparison test, both of the series do the same thing, so then we can conclude that the original series of a sub n also converges. Hey guys, a little behind the scenes. This is what I was taking notes on and screen recording. And then I have my hard copy calc notebook over here for reference. And my dog, who gets a little anxious, wanted to get up and sit next to me, so she's been here while I've been recording. But yeah, just want to say thanks for watching, and please subscribe to my YouTube channel and hit the like button. I appreciate it. Okay, take care.